Let's say we have a system of linear equations, and I want to try to find some solutions and stuff. One neat trick we can do is pull out the coefficients here and put them into a matrix, and then for this equal sign, I'm going to put a little bar like this, and on the right side, we'll be able to put the answers. So we'll put 0, 8, and 10, and then the coefficients would be like 2, -2, 3. Here we have 0, 2, and -8. Here we have 5, 0, and -5. Now we've created a matrix out of these. We can label these sort of as row 1, row 2, row 3, and then here we have column 1, column 2, column 3, and column 4. And as far as vocab goes, this little thing here is just called the coefficient matrix, just this left side. And then if you include that part, it's actually called the augmented matrix. So those are just some vocab words pertaining to these matrices. And we can also translate this into vector form as well. So we could say vector 1, vector 2, and vector 3, that would be corresponding to these three columns here, is going to be equal to the solution vector, which we'll call B over here. And we can actually expand this out a little bit. So we'll take the vector 1, which is supposed to be this column. We'll say 2, 0, and 5. And then let's go back over here and realize that it was supposed to be multiplied by some x. So let's put the x in there. We'll call it x1 though. And now we can go ahead and add the next vector, which is going to be vector 2. Vector 2 is this one, -2, 2, and 0. And now we can go ahead and go back to our y here, multiply it by the y's, but I'll call it x2 instead of y, just to make it a little bit more interesting. And then for the third one, it's going to be v3, so we're going to add that one in there. That's going to be this one, 3, -8, -5. 3, -8, -5. And we'll link this up with the z, but of course, we'll just call it x3. And we'll set this whole thing equal to the final component, which is simply just going to be 0, 8, and 10. But that's going to be our b vector, so I'll call that the red ones here, 0, 8, and 10. And so now we can see how we've expanded these into three different ways of looking at the same equations. Well, if this here is called the vector equation, well, let's see if we can combine the vector and the matrix form together. So we're going to call it A, and then we're going to have an x here, call that a vector. We're going to set that equal to the b vector, which is going to be this one here. And we'll call this the matrix equation. We have our matrix equation here. Let's plug those into a matrix and some vectors. So with this matrix A, we're obviously going to label those A's, and I'll have 6 A's in here. This one here, we're going to start counting the rows first. So like 1, 2, 3, here's row 1 and row 2, row 1 and 2, and row 1 and row 2. And then we'll go across this way and count the columns, 1, 2, 3, 4. So we'll put 1, 2, 3, 1, 2, 3. And now we sort of have our coordinates there. For the x's, it's just going to be x1, x2, and x3 like this. And they sort of get distributed here, here, and here, as you can see. And then for the b, we're just going to put those 0, 8, and 10. And this is the matrix equation. In order to get an answer to this system, we're going to try to simplify it into echelon form first. Echelon just simply means steps. So we kind of want to see a step-like formation over here. And I'm going to make a new example, but here are the numbers. So we're going to have 2, 4, 0, and then there's a 7 here. And then we have a 0, and a 3, 2, and 5. Here we have 0, 0, 0, 6, and here is just a row full of zeros. And we can see how the steps are formed if we started here, and we take a step down here, we come across here, and we're forming sort of a step-like formation. Now the characteristics of an echelon form matrix are that we're going to have zeros before any leading entries. So that would be these things over here. This is going to be a leading entry right here in the first spot right there, and then we have a leading entry right here, and then technically you consider this a leading entry, but it's in our answer column, so this is making it an inconsistent solution. We'll see what that means later. We're going to ignore this leading entry just because it's in the answer column, but we're also going to note that we would have zeros below any leading entries. And so you can see how we have zeros below these leading entries, and there's a 0 below that one as well. Final note is we also have all 0 rows at the bottom. And of course, all 0 rows are at the bottom here. And this is what we can call echelon form. There's going to be many orientations, many versions of the echelon form, because we're not quite as reduced as possible. So you can get to different stages of this and it'll still be called echelon form. This is called the forward phase of the reduction process. In order to reduce this further, we need to get to reduced echelon form. So I'll look something more like this. We'll have a 1, then we got a 0, and we'll put the 2. Here's another 0. And then we have 0, 1, 3. Here's another 0. 0, 0, 0, 1, and 0, 0, 0, 0. Now this is a unique form of this matrix. We can't simplify this any further. And you can see how mainly the main differences from here and there. We already had zeros here. We added in zeros above in order to turn everything into ones and zeros over here. So this is called the backward phase. We have some more criteria we need to keep track of. So let's mark that we need all leading entries are 1. And we can see that that has happened here. This became a 1, this became a 1, and this little thing became a 1. Let's also note that we need all leading columns to be only 1s and 0s. 1s and 0s. And that's mainly the key here. So we can see that this column has only 1s and 0s, this column has only 1s and 0s, and we even got this column to have just 1s and 0s to help clear out some of those numbers. But we've noticed how this particular column here, this column contains the free variable. So x3 is the free variable. If you have a free variable, that means that you might have infinite solutions to this system, in which you have to parameterize x3 as t. We're going to see how to do that later. But for now, we'll just claim that the pivots are going to be your basic variables. Now let's define a really important concept. It's called rank, and this is simply the number of non-zero rows in echelon form. So if we go back to our echelon form, we could see how if we were to cover up the augmented matrix, we see that the A matrix just by itself has 2 non-zero rows, and so therefore the rank is 2. If we include the whole matrix here, then we see that we have 1, 2, 3 non-zero rows, so the rank is 3. Over here, same thing. We can cover this up and we'd see that this left side is just going to have 2 non-zero rows, whereas the right side is going to have 1, 2, 3 non-zero rows. I'd like to also define this matrix A here as having dimensions of m times n, where m is the number of rows and n is the number of columns. Now m and n actually correspond to the dimensions of 2 vectors. N is actually dimensions of the x vector. So we're going to put that here, x1, x2, whereas m is the dimensions of the b vector. B1, B2. We'll see how that comes into play in just a moment. So how do I know if a system of equations has only one solution, which implies that the lines sort of intersect at one particular point right there? Well, the first thing I need to do is look at the rank of A and see if the rank of A is equal to n. If the rank of A is equal to n, then that means that the number of non-zero rows in A is equal to the number of x's that we had. If we had 3 x's, we're expecting 3 non-zero rows here. However, we only got 2 of them in just the A. Of course, there's 3 in the AB, but we're looking at just the A component here. We see only 2 columns of non-zero rows, and yet we had 3 x's. So technically, this is not going to have one solution. Well, let's just pretend for a second that we had something like a 1 right here. And so in that case, we would see that we have like a question mark is going to be equal to some sort of B over here. That means that something, it doesn't have to be 1, but something is equal to some other number. And it's important to note that this question mark cannot be equal to 0, because if 0 equals B, then we have no solution. That's the next step. But if we happen to have a 1 right there, like right there, then we can easily just say that this particular variable here, x3, is equal to 1 in this particular situation. But it wasn't. This was supposed to be 0. And so that actually leads us to no solution. Now let's see when we get no solution from our system, and that would imply that we have something like parallel lines or skew lines where they would never intersect. In order for this to happen, then the rank of A must be less than the rank of AB. And so we can see here how if we have the rank of AB is, for example, 3, then that means that we have 3 non-zero rows in the AB thing, in the rank of 3. But the rank of A is only 2. So that means that we have a full 0 row in A, but it actually equals some sort of a number in B. And that gives us this setup where 0 is equal to question mark. Remember, question mark is not equal to 0. So 0 equals something. And when we know that's not true, because 0 plus 0 plus 0 does not equal 1. And so that actually gives us no solution here. Let's see if we can get infinite solutions out of our system here. That would mean that the rank of A is going to be equal to the rank of AB. So we don't have infinite solutions, but there's an extra variable somewhere because our x dimensions over here, 1, 2, 3, just happen to have an extra variable that we need to use somehow. And so we're going to parameterize it. We're going to call it t. Let's go back to our little example here. But I'm going to switch this to being a 0. So that way we could see how the rank of A equals the rank of AB. We got a rank of 2 here and a rank of 2 there. But now we have on this row, we have a row of all zeros, implying that 0 equals 0. And we kind of have this third variable here. It should have been here. It should have been a 1 right here. But it didn't work out that way. So now it's kind of this random x3. We're going to call it t. We're going to parameterize it. And we're going to put it along a timeline. So here's like the timeline, the t line. And all the other lines just lie on that line as sort of a scalar multiple. And so they're all going to be on that same line. So we got infinite solutions here based off of whatever we decide to put in here for t. Now I'm going to try to put the answer in parameterized form. So I'm going to solve for x. That's the x vector. So we have our variables that we're trying to solve for. I'm going to set that equal to, think about y equals mx plus b, where the b would be the y-intercept. I'm going to claim the y-intercept here is going to be the xp vector. That is the particular solution. So let's think of that as just like 0, 0, 0, the origin, right? And then over here, we can go and add in the parameterized variables. So we'll go in xt. x3 is supposed to be t now. And then we'll plug in the d. And d is going to be the direction vector. So you could think of this sort of as, this is like your variable x, and this is like m, where it's like mx plus b, yeah? Y equals mx plus b. It's just in a slightly different form here. Now let's try to define linear dependence and linear combination. We can kind of see from this what a linear combination is. We're going to take our variables, which would be x1, and our vectors, we'll call it vector 1, plus x2, and vector 2, and then plus x3 and vector 3, and yeah, add these all up, and they're just going to equal some kind of a b vector, right? So this is a linear combination. Now it also turns out that, hey, if I covered up all this right here, I could see that b is simply a scalar multiple of this v right here. So it turns out that scalar multiples are actually dependent. Now a linear dependent set means that at least one of those vectors from the set is a combination of vectors. So if your vector b, which is a linear combination, is inside of the set of vectors, then that guarantees that this one was created from a linear combination, and so that set is going to be linearly dependent. Linear dependence also means that you're not going to get a unique solution. You're either going to get no solutions or infinite solutions. And we're going to try to introduce span here real quick. So the span of A1, A2, A3 is going to be these three vectors, 1, 2, 3 here. The span of those vectors is going to be all the possible answers that you can get out of this equation. So if we set up the equation AX, then the span of these A vectors that are inside matrix A is just going to be all the possible solutions you can get out of there. So you might get the 0 vector out of that. That's totally possible. You could get one of those A vectors out of there, right? It's totally possible. Or you could get some sort of a new unique B vector out of that, and that's totally possible. So all the possible images that you can form with this particular equation is going to be the span of A. So technically the x's could be all zeros or 0, 1, 1, or any kind of numbers that you could plug in for x's that essentially gives you like infinite solutions over here on the right, and that's the span of the A vectors. Now I'm going to try to draw a visual representation of span. So let's say that we wanted to get into the third dimension. So this would be like I, j, and k. And then we would have the span of three vectors. We'll call them this vector, and this vector, and this vector. Now, it's important that these three vectors are linearly independent. And we'll see what that means in a second. But if these are linearly independent, what I can do is, usually we do this with I, j, and k vectors. We kind of multiply those by some number, and we can get the entire range of 3D, the three dimensions, which we'll call R3 here. But let's say we wanted to form some kind of a vector in R3, and we'll say, oh, I want that vector. What I have to do is I have to take these three independent vectors, and I have to create a combination of those vectors by saying, okay, well, I'll take x1 times this first vector plus x2 times this other vector here plus x3 times that third vector. And then if I do that, I'm going to get this vector. Bam. And so this is actually a combination from these three vectors, which were all independent. So these independent vectors turn into this vector through linear combinations in 3D. Now we can make the statement that three linearly independent vectors span R3 in 3 dimensions. We could say that 2 linearly independent vectors span R2, 4 vectors span R4, as long as they're linearly independent. And this is exactly what that means. It means that you kind of have this I, this j, and this k, that you can create this R3, this 3-dimensional space. It doesn't have to be ijk. We usually do it with ijk, but we can also just do it with any old random vectors. And that's what spanning is. We've seen that linear dependence means that you can be formed of a linear combination of other vectors. But let's see what linear independence means. That means that you could set up this equation, x1v1 plus x2v2 plus x3v3, and you could set that equal to 0. And the only solution for this is going to be x equals 0. If x equals 0 is the only solution that you can find to this particular equation for those three vectors, then you know that the columns or the vectors of A are linearly independent. Now let's analyze this equation a little bit further. So we're going to have something like AX is going to be equal to 0. Now this has always a solution of x is going to be equal to 0. This is called the trivial solution, and it's always going to work, right? But it could be that we have a non-trivial solution at some point, and this would happen if the rank of A is less than n, meaning that we have like an extra variable, x4, x5, that we weren't able to solve for, and so you could possibly get infinite solutions out of that. This would be dependent instead of independent. And of course, to find that solution, you're just going to row reduce A0, reduce that little matrix there, and you're going to solve for x. Do that. That's going to be a dependent solution, but you could totally find that if x equals 0 is not the only solution. Now I've set up an example where the rank of A is equal to n, where you have a rank of 2 here in the A matrix, and we only have 2 x variables here. If this situation happens, then we know that we have a linear independent columns of A. we know that n columns of A span Rn. So that means that we're going to get a two-dimensional area out of that. And then we also know that x equals 0 is the only solution to Ax equals 0. So we know that the trivial solution is the only solution possible here. We also know that we have no free variables. All variables are defined. And of course, there is a possible no solution. And you can see how if this last column here, or this last row of B was an actual number, then you would get 0 plus 0 equals some number, and that would be no solution. But if this was just a 0, then 0 plus 0 equals 0, and that's totally fine. Okay, so this is the rank of A equals n. Now let's see what happens if the rank of A equals m. So the rank of A here is going to be 2, and that leads us to 2 entries in the B vector here. So what this implies is that we have m columns of A span r to the m now. So we can see how r to the m is just 2, and so this is going to be a two-dimensional area that it's going to span. So they actually span the same area, a 2 by 2 and a 2 by 2, even though we have different sets of x's here. It's interesting. We also have all b's that are made here. All those b's are linear combinations. Linear combinations of these vectors here. And it also guarantees that you're going to find one x, at least one x, for every b. For every b. Let's remember that in this particular case, we had possible no solutions. So that means that there might be a b sitting out there. Then you can't make a combination of these vectors to create that, like we did over here. But in this situation here, every single b was a combination here. So you can't have no solutions. But what you could have over here is infinite solutions. So here there's actually possible infinite solutions, because you might have a vector over here that you can take multiple different combinations to create that same vector. And so this is the difference between rank of A equals n and rank of A equals m. Now we've seen how we can represent a system as linear equations, as a matrix, as vectors in this form, vectors in this form. We even have a matrix equation that we could do, set it up like this if we wanted to. And now we can do another type of notation called transformations. We could say that the transformation of this x vector that we plugged in here, and we can actually just scale that by our matrix A, and then we'll come up with some sort of B images. All right, basically you're just scaling the vector x by A and creating a bunch of different images out of that, right? So we can call the set of all x's are just going to be the domain, and we can call the set of all b's, all these images that we're getting from here, those are going to be the codomain. Now there's many kinds of transformations. We're going to focus on the linear transformations. One way you could check to see if something's linear is to plug in the 0 vector, and you should get the 0 vector out because 0 times anything is 0. So you plug in your 0 vector for x, no matter what kind of matrix you multiply that, you should always get the 0 vector out of that. The next property of linear transformation is scalability. So if you take a vector that has been scaled, like the CU vector, then you should be able to just take the vector by itself and then transform it and then scale it later. So whether you scaled it before the transformation or after transformation, you should still get the same answer. And the third property of the linear transformation is that it is commutative. So you should be able to plug in a u plus a v, and then whether you add them before the transformation or whether you add the actual transformation separately like this, you should still get the same answer out of that. Now let's see when a transformation is 1 to 1. The problem is we have to use up all these x's, but we have a rule that we can use at most 1x per b. So if we start matching these over, then I can only use 1x per b. So 1x per b. The interesting thing is that I can have some B's over here that didn't get matched up because this is at most 1. Now this can happen if the rank of A is equal to n. Let's compare that for when the transformation is onto. The rule is we have to use at least 1x per b. 1x per b. So if we start mapping over here, and we see it, we have to first of all use up all these x's, but we have to use at least 1. So all these b's need to be used up as well. Put them over there, put that one there, and now we can even put all 3 of those on that one. And this will work out. And this can happen if we have a rank of A is equal to m. And now we can visually see what possible no solutions means or possible infinite solutions means. Here we have just 2 floating b's, so there's no solutions over there. And here we have multiple x's for a single b, so that could be possibly infinite solutions. And the last thing we're trying to squeeze in here is how you might be able to reverse engineer the A if you happen to know you can transform your E1, E2, and E3 vectors. So these just correspond to an identity matrix. So in this situation in 3D, you'd have something more like 1, 0, 0, 0, 1, 0, and 0, 0, 1. And since those are just multiplying by 1, you could just kind of basically figure out what that was multiplied by and figure out what your A matrix was. And so this is the basics of linear algebra.